All right, today we are going to be moving on to section 2.9. This is the calculus of hyperbolic functions. Let's first define what these are. So if you remember, the reason sine and cosine are really nice is because if I drew the unit circle, y'all about to see my circle skills here. Unit circle, that's a circle. Then any point on here is going to be the point where the first part's going to give me the cosine and the second part's going to give me the sine, right? That's what we know from trig or pre-calculus or whatever class you took before calculus one, right? Hyperbolic, instead of it being on the circle, what hyperbolic means is that it's going to be on a hyperbola. So it's going to be like, instead of a circle, it's going to be like this, and every point is going to be hyperbolic cosine, hyperbolic sine. That's really all that this means. Okay. For the purposes of this class, a really nice way to define the hyperbolic trig functions is like so. So hyperbolic sine, which is sine h, right? Hyperbolic sine is going to be e to the x minus e to the negative x divided by 2. Hyperbolic cosine is going to be e to the x plus e to the minus x divided by 2. Hyperbolic tangent is e to the x minus e to the minus x over e to the x plus e to the minus x, and on and on and on. So hit pause or whatever. These are how I'm going to define the hyperbolic trig functions for the purposes of calculus 2. Okay. Now, why is it helpful to write them like this? That is because now it is not hard to take the derivative because I know how to work with e, right? So I'm going to do that. We are going to take the derivatives. I'm going to show you the first one. The rest of them will follow straight from that. So let's take the derivative of hyperbolic sine. Let me get a different marker. The derivative of hyperbolic sine of x. Well, we just said hyperbolic sine is defined as e to the x minus e to the negative x over 2. Dividing by 2 is like pulling out a 1/2, right? So I'm going to bring a 1/2 out front. That's going to make it kind of nicer. And then I can just take the derivative of each part of this and subtract them. As soon as I find a marker that works. So that's 1/2 out front. The derivative of e to the x we know is just e to the x. That's why we like e, is because e just stays e. And then the derivative of e to the negative x, well, to start with, e just stays e, so e to the negative x. However, since I have e to the negative x, I need to times that by the derivative of the negative x, which is negative 1. None of my markers are working. So what that is going to do is, since I'm doing minus the negative 1, that's like saying plus 1. So e to the x plus e to the negative x. Since it's 1/2 times that whole thing, I can write that as e to the x plus e to the negative x over 2, which, if I look at that is equal to hyperbolic cosine. So the derivative of hyperbolic sine is equal to hyperbolic cosine. If I use those same thought processes on the rest of them, I get the following derivative rules. The derivative of hyperbolic sine is equal to hyperbolic cosine, which is what we just did. The derivative of hyperbolic cosine is equal to hyperbolic sine. The derivative of hyperbolic tangent is equal to hyperbolic secant squared. The derivative of hyperbolic cosecant is equal to negative hyperbolic cosecant times hyperbolic cotangent. The derivative of hyperbolic secant is equal to negative hyperbolic secant times hyperbolic tangent, and the derivative of hyperbolic cotangent is equal to negative hyperbolic cosecant squared. These are very close to the derivatives of the trig rules we learned in Cal 1. Just watch what the signs are. So like I said, we could find each of these rules by doing what I did here. I just showed you the first one, but it works for them all. Okay. So let's work some examples using these rules. Example number 1, evaluate the following derivatives. Part A asks for the derivative of hyperbolic sine of x squared. Example 1, part A, it wants the derivative of hyperbolic sine of x squared. Well, from the rules I have, I know that the derivative of hyperbolic sine is equal to hyperbolic cosine. So to start with, I know that's hyperbolic cosine of x squared. But since I have an x squared in here, I need to multiply that by the derivative of x squared. The derivative of x squared is 2x. That's it. That's all I've got to do. 1b asks us to find the derivative of hyperbolic cosine of x, that quantity squared. So let's look at that. The quantity hyperbolic cosine of x squared. Well, remember from the chain rule, I do the outermost part, right? And the outermost part here is the squared. So I'm going to do that first. Remember, bring our power down front and then decrease our power by 1, which is going to make my new power a 1. So this is a good start. Bring my 2 down front. But I'm saying hyperbolic cosine squared, which means I have to now find the derivative of the hyperbolic cosine, which I know is hyperbolic sine. So multiply this by hyperbolic sine. There we go with that one. And then 1c asks us to find the derivative of hyperbolic tangent of x squared plus 3x. The outermost part here is the hyperbolic tangent. The derivative of hyperbolic tangent is hyperbolic secant squared. So hyperbolic secant squared of, leave the inside part, but then by the chain rule, I have to times that by the derivative of this part. The derivative of x squared plus 3x is 2x plus 3. Remember to put parentheses, otherwise it isn't right. So once again, this is just using the chain rule, just like we did a lot of in section 2.7. Example number 2 asks us to evaluate the following antiderivatives. And we're going to be doing these 3 examples right here. Example 2a. Integral of x hyperbolic cosine of x squared dx. Well, if this was just hyperbolic cosine, it wouldn't be very hard because since I'm taking the antiderivative, I'm taking the derivative and then I'm going to go backwards, right? So if it was just hyperbolic cosine, I would know going backwards it would be hyperbolic sine. But this is hyperbolic cosine of x squared. So it would be really nice if I could let u be equal to x squared and the derivative be there. So u equal that x squared. In order for that to work, du would have to be 2x, which is fine because I already have the x here. I just need a 2. I forgot the dx right here. I just need a 2. I'm going to pause for 1 second. Okay, I believe I have found a marker that works. Let's see. So this has to be 2x dx, which is okay because I already have x right here. I just need a 2 out front, which I can put there as long as I put a 1/2 out front. So this is going to give me 1/2 integral 2x dx becomes du. So I just have hyperbolic cosine of u. If the derivative is hyperbolic cosine, I know I got that from hyperbolic sine. So this is 1/2 hyperbolic sine of u plus c. Plug back in what the u was x squared. So this is 1/2 hyperbolic sine of x squared plus c. Remember the plus c, it is important, it's got to be there. Now let's do example 2 part B. Example 2 part B is the integral of hyperbolic tangent of x dx. Once again, the idea here is I want to take the antiderivative, so it would be really nice if there was a derivative that was hyperbolic tangent, but in looking at our rules, none of them are. But remember, just like with regular trig, hyperbolic tangent is equal to hyperbolic sine over hyperbolic cosine. I can see that here, right? If I did hyperbolic sine over hyperbolic cosine, it would give me hyperbolic tangent. So what this means is I can write this as the integral of hyperbolic sine of x over hyperbolic cosine of x dx. Doesn't seem like this really helps me, but notice here, if I let u be equal to hyperbolic cosine, du would have to be hyperbolic sine, which I have on top. It would not work if I let u be equal to hyperbolic hyperbolic sine, because in order for that to work, du would have to be hyperbolic cosine, which I only have in the denominator, which I don't really like. I want it in the numerator. So this would not work. I'm going to let u be equal to hyperbolic cosine, just so that du is in the numerator. So what this is going to become, hyperbolic sine times dx is now the du, and hyperbolic cosine is my u. So this is just integral 1 over u du, which we know is equal to the natural log of the absolute value of u, plus c. Plug back in what the u is. We know u is hyperbolic cosine. C. So this is using a lot of our trig stuff, and this is using a lot of what we did in section 2.7, antiderivatives of 1 over u. Let's look at example 2c. 2c, hyperbolic sine cubed times hyperbolic cosine dx. Let's do that one. Hyperbolic sine cubed times hyperbolic cosine dx. So for this one again, this one looks weird because I'm cubing hyperbolic sine, then I have another thing. Like, it's just a lot happening, right? So it would be really nice if I could rewrite this into a way that's not as complicated. So I have something cubed. If it was just something cubed, it wouldn't be hard, right? Because we have the power rule. So it'd be really nice if I can let u be equal to that hyperbolic sine, because then I would just have u to the third, right? In order for that to work, though, du would have to be the derivative of hyperbolic sine, which is hyperbolic cosine. And that's okay, because look at what I have right there, hyperbolic cosine. So this would work. So this becomes integral. Hyperbolic sine is now a u, so this is u cubed. Hyperbolic cosine times dx is the du, which isn't hard. So antiderivative of u to the third, add 1 to the power, gives me u to the fourth, over my new power, which is 4, plus c. And we already said u is hyperbolic sine. So there we go. So just like with trig, we have inverse hyperbolic stuff. So I have some rules here. So the derivative of inverse hyperbolic sine is 1 over the square root of 1 plus x squared. The derivative of inverse hyperbolic cosine is 1 over the square root of x squared minus 1. The derivative of inverse hyperbolic tangent is 1 over 1 minus x squared. The derivative of inverse hyperbolic cosecant is negative 1 over the absolute value of x times the square root of 1 plus x squared. The derivative of inverse hyperbolic secant is negative 1 over x times the square root of 1 minus x squared. And the derivative of inverse hyperbolic cotangent is 1 over 1 minus x squared. So these are just some more rules I'm going to have here. So let's do these examples. Example number 3. A asks us to find the derivative of inverse hyperbolic sine of x over 3. So let's work on that. Derivative of inverse hyperbolic sine of x over 3. So I know our rule for the derivative of the inverse hyperbolic sine is 1 over the square root of 1 plus x squared. So I'm going to use that because the inverse hyperbolic sine is the outermost part. So I know that's going to be equal to 1 over the square root of 1 plus the inside is x over 3, so make sure to use x over 3 for that. But then I have to times that by the derivative of the inside part. The derivative of x over 3 is 1/3. So multiply that by 1/3. Again, this is just using the chain rule. Part B asks us to find the derivative of inverse hyperbolic tangent of x, that whole quantity squared. So again, I'm starting with the outermost part. The outermost part is the squared part. So I'm going to start with that. So bring the 2 down, which gives me 2 hyperbolic inverse tangent of x. My new power, remember I decreased this by a 1, which would just make it a 1, so that's good. Inverse hyperbolic tangent is what was being squared, so I also need to multiply this by the derivative of that. The derivative of the inverse hyperbolic tangent is 1 over 1 minus x squared. Easy enough. Once again, just chain rule. And then the last one for derivatives is the derivative of inverse hyperbolic cosine of 3x. Once again, the outermost part is the inverse hyperbolic cosine, so I'm going to use that rule first. That's going to be 1 over the square root of x squared minus 1 over the square root x squared. Inside I have 3x, so it's actually going to be the quantity 3x squared minus 1. But then times it by the derivative of this stuff right here. That stuff, the derivative of the 3x is just 3. So here we go. Now let's also use these rules to take the antiderivatives. So example number 4 asks us to do just that. 4a is the integral of 1 over the square root of 4x squared minus 1 dx. So looking at our rules, 1 over something squared minus 1 is what I have, right? 1 over something squared minus 1. That looks a lot like this, right? It looks a lot like this. The only change is that I normally only have x squared. So that's how I want this to look too, because here I have 4x squared, which I don't like. So I'm going to look at this and say, okay, what is being squared here? Well, in order to get 4x squared, I can square 2x because 2 squared would give me the 4 and then x squared. So we're going to let u be equal to 2x. Again, because right here I just want something squared. What is being squared here? 2x. For that to work, du would have to be 2, which I can do, right? I can put a 2 here as long as I put a 1/2 out front. So this is going to become 1/2 integral 2 dx is now the du. So it's just going to be 1 over square root. Once again, this is 2x squared. So this is just u squared minus 1 du. Well, now this looks exactly like that. So this is going to be equal to 1/2 inverse hyperbolic cosine of u plus c, and we said u was 2x. So 1/2 inverse hyperbolic cosine of 2x plus c. Once again, this first step, I want right here just a singular term squared. So 4x squared came from squaring 2x. That's why I get hyperbolic cosine of 2x. That's where I get that from. Try to do the same thing here with b. b is the integral of 1 over 2x times the square root 1 minus 9x squared dx. So the same thing here. I want to see if there's anything that looks kind of like that. So looking at our derivative rules, I can see that kind of looks like this. Kind of looks like this, right? Because I have an x out front and then a square root 1 minus stuff squared. So it looks a lot like this rule does. So let's try to make it look just like that. Okay. So first things first, I have this random 2 out front. There's no 2 out front here, right? No 2 out front. So let's bring out a 1/2 just to help us out. And then again, inside of here, I just want something squared, right? I just want something squared right here. So what did I square for 9x squared? You would have squared 3x. So for du, I would need a 3 dx. So once again, it's okay if I put a 3 up here, as long as I put a 1/3 out here. So multiplying this by 1/3 actually would give me 1 over 6. But I can't stop just yet, because if I brought this 2 out front, notice here, if this is u squared, I want this to be a u, because that's what my rule right here says, right? In order for this to be a u squared, I would need this to be a u. Well, my u is 3x, so I need a 3 right here. Only way I can put a 3 there is if I put a 3 on top, which would then bring this to being 1/2 integral. The 3 would then fall in with the dx, so that's okay. And so I get 1 over 3x is my u, square root of 1 minus, this is 3x squared, so u du. Now it looks exactly like this. Oh, not quite actually, because this actually has a minus sign. In order to have a minus sign up top, I need one in front too. So this is going to become negative 1/2. That rule is inverse hyperbolic secant of u plus c, and my u is 3x plus c. Remember, always true, if something doesn't make sense, you can let me know, and that's fine. I can help you out. Last example, for c, I wonder if I can make it fit right here. I'm gonna. Integral 1 over the square root of x squared minus 4 dx. So once again, I'm going to look on here and see if there's a rule this kind of looks like. It kind of looks like this rule, right? 1 over the square root of something squared minus a constant. The difference is the constant here has to be 1. This constant is 4. So there's something I've got to do there, okay? Again, this rule calls for a 1. I have a 4, so that's no good. So what I'm going to do then is I want to make this a 1. So I'm going to factor out that 4. So this is going to be integral 1 over the square root. I'm factoring out a 4, which would mean this first term would turn into x squared over 4 minus 1 dx. Why is that nice? Because now I can take the square root of 4. Square root of 4 is 2, which gives me a 2 in the denominator. So I can pull out a 1/2. Again, because the square root of 4 is 2, it's in the denominator, which makes it 1/2. Integral 1 over the square root of x squared over 4 minus 1 dx. Now it looks like this rule. So once again, just like on all of these, I want to see what's being squared right here. Well, to get x squared over 4, I would need to square x over 2. The derivative of that is 1/2. And look at that, I already have a 1/2, so I don't have to change it. I'm good. 1/2 dx becomes the du, so all I'm left with is integral 1 over the square root of u squared minus 1 du. Integral of 1 over the square root of u squared minus 1 is inverse hyperbolic cosine of u plus c, and our u was x over 2. So inverse hyperbolic cosine of x over 2 plus c. Once again, you may want to know where did this 1/2 go. Since the du is equal to 1/2, it blended in with the dx to become du. As always, if any of that does not make sense, please let me know. I will be happy to help you out.